Let's start with a simple common problem, calculating the mean value of two variables from a dataset. On the top, I'm carrying out this task using pandas. On the bottom, polars. Same data, same results. I personally favor polars as the code reads like a sentence. From this data frame, select a target, petal length and petal width, then group by target, then aggregate the mean of all the columns. Once you get comfortable with this style, you may find it hard to go back to pandas. Polars is a newer data frame library built for speed and readability. It won't replace pandas. Pandas has a massive ecosystem and broad compatibility. But for data manipulation, Polars offers a modern alternative worth learning. And if you're in marketing or business development, readable code makes it easier for you to tackle complex problems or describe and verify what you want from an AI assistant. Let's get started. This video builds on everything we've covered so far: installing Python, setting up a virtual environment, JupyterLab, and the pandas fundamentals from the last video. If you need to catch up on any of those, links to the earlier videos are in the description. In JupyterLab, create a new notebook by clicking on the Python tile on the launcher, then right-click on the tab and rename it. We'll start by creating the exact same data frame from the last video, but this time with polars. First, we import polars as PL. Now, let's create the same student grades data frame that we built in the last video. And then we can display it. The syntax for creating the data frame is almost identical. Same dictionary, same list, but look at the output. Polars shows the shape, 3 rows, 6 columns, and it displays the data type directly beneath each column header. I64 is a 64-bit integer, str is a string. Polars is strict about types from the start. There's also no index column on the left. Polars doesn't use row indices the way pandas does. In pandas, we selected columns with bracket notation for a single value, or by using a list for multiple values. Polars uses an explicit select method. We can type polars_df .select and then include student as the argument. Selecting multiple columns is just as clean. We simply pass an additional column name as arguments. Here, I've typed polars_df .select, and now I include the A column and the student column. While passing columns names as strings will work, it isn't the recommended approach. Polars is built around expressions, and pl.call is one of the foundations of that system. We simply include pl.call for both the A column and the student column. This gives us the same result. Passing column names as strings works for simple selections, but the pl.call function is what you want to use as a habit. It becomes powerful when you start chaining operations, filtering, computing new values, renaming, all within the same expression. You'll see it everywhere from here on. Polars doesn't have iLook. There's no row index to reference. Instead, you use slice to select rows by position. For example, we have polars_df .slice, and we include 0, 1. The first argument is the starting row. The second is how many rows to return. This gives us the first row. Polars also has a head method that works just like pandas. It returns the first 5 rows by default, and we'll use this below. Now, let's look at the much more useful way to select rows, filtering. Let's load the iris dataset through pandas and converted into a Polars data frame. This is a common workflow. Pandas has excellent file reading capabilities that Polars can leverage. So for this example, I'll import pandas as PD. And then from the scikit datasets module, we'll import the load iris dataset. We need to extract the data frame. And now we can use the pl.dataframe function to convert this into a Polars data frame. You'll notice I'm using iris_pl_df with _pl_ in the name. This is simply to make it clear we're working with a Polars data frame, and in a real project, you most likely would just call it iris_df. The extra label is just for teaching purposes, so we can keep pandas and Polar examples distinct. So let's take a look at what we're working with. A quick way to do this is simply using the head method on the data frame. Now let's filter. In pandas, we had a fairly complex expression, brackets within brackets. In Polars, this is much more readable. I'm including my code inside of parentheses so that I can do line breaks. And here I have the iris Polars data frame, and I'm simply going to filter on the target column equal to 1. You can read this aloud from iris filter where the target column equals 1. The filter method is one example where Polars starts to feel more natural than pandas. Again, notice that we've wrapped the entire expression in parentheses with the data frame on one line, the filter on the next. This isn't required for a single method, but it's a habit worth building now. As you chain more methods together, this style keeps each step on its own line and makes your code much easier to read. You can also combine multiple conditions with an ampersand. So here I have my iris Polars data frame. I'm going to use the filter method. And now I'm going to include two conditions. I'm going to look for the target column equal to 1 and also the sepal length column greater than 6. Notice that each condition needs its own parentheses. As a quick reference, the Boolean operators you will use most often with filter are the ampersand for and, the vertical line or pipe for or. The comparison operators work the way you expect. Equal for equals, the explanation point equal for not equals, and then the combination of either greater than, less than, or greater than equal or less than equal. Grouping and aggregation in Polars uses a similar pattern to pandas, but this syntax is more explicit. Here, I'm taking our iris Polars data frame. I'm going to group it by the target column. And now I'm going to use the aggregation function, looking at both the mean and standard deviation for the sepal length. Each aggregation is a polar expression. The PL call selects the column. The dot mean computes the mean, and the dot alias gives the result a readable name. You'll also notice that we're using PL column inside the group by, keeping our expressions consistent throughout. If you compare this to pandas, the group by ag produces a multi-level column index that often needs reshaping. Here, you get a clean, flat result. Above, we used a single column, but you can aggregate multiple columns in a single call. So here, below, I've looked at sepal length, petal length, and a count of the target values. As I previously stated, I developed a personal preference for polars, but pandas isn't going away. Here's when you'll still reach for pandas. Many established Python libraries scikit-learn stats models can accept a pandas data frame as input. When that happens, Polars makes it easy to convert with the toPandas method. We simply take our data frame and append toPandas. And going the other direction, we can pass a pandas data frame directly into the Polars data frame function. And this is the same constructor we've been using. So again here, I can take my Polars data frame function, pass the pandas data frame as the argument, and now we can look at the type. I've also found that pandas has a broader support for reading files. Read CSV, read Excel, read HTML, read SQL, and these are some that Polars may not cover as well. My personal workflow is to use pandas for loading data and then converting to Polars for manipulation. I find the switching cost to be minimal. We've now covered a lot of the same ground with both pandas and Polars. Creating data frames, selecting columns and rows, filtering, grouping. You've seen how Polars uses select, filter, and group by with explicit expressions that read more like instructions than code. In the next video, we'll work on a practical problem, reshaping data from a format people can read into a format your code can work with. We'll also introduce feature engineering, which is simply creating new columns from existing data. So save your notebook and we'll pick up from there.